In October 2025, a spacecraft designed to photograph the surface of Mars was pointed at something moving through deep space instead. What it captured turned out to be a genuinely impressive technical achievement, not proof of anything unnatural, not evidence of intention or design, just a real difficult engineering feat that added a valuable new angle to one of the most exciting objects astronomers have studied in years. This is the real story of what China's Tianwen-1 spacecraft actually saw and why it matters. Let's start with the object itself, because context matters here. 31A TLAS is an interstellar comet, discovered in July 2025 by the Atlas Survey Telescope Network. It's only the third confirmed interstellar object ever detected passing through our solar system, following Oumuamua in 2017 and 2I Borisov in 2019. Its trajectory is hyperbolic, meaning it's moving too fast and too straight to ever be captured by the sun's gravity. It came from outside our solar system, is passing through, and will leave again permanently, never to return. Because objects like this are so rare, and the window to study one is always brief, astronomers around the world scrambled to point every available instrument at it once it was confirmed. Hubble observed it. James Webb observed it, using both its near-infrared and mid-infrared instruments to study its chemistry in detail. Ground-based observatories tracked it constantly. And then space agencies started looking at something else entirely. Which spacecraft already out in the solar system, built for completely different missions, might also be able to get a look at it? That's where Tianwen-1 comes in. Tianwen-1 is China's first interplanetary mission. It launched in July 2020 and entered orbit around Mars in February 2021, carrying an orbiter, a lander, and China's first Mars rover, called Zhurong. The orbiter has been circling Mars for years since then, and its main camera, called HiRC, the high-resolution imaging camera, was built to do one specific job: photograph the surface of Mars in extremely fine detail, capturing features as small as roughly half a meter across from low orbit around the planet. That's a camera engineered for short, precise exposures of a bright, close, stationary surface. Nothing like what would be needed to photograph a small, extremely faint object, moving rapidly through deep space, tens of millions of kilometers away. But in early September 2025, once 3I ATLAS's trajectory became well understood, the Tianwen-1 team began exploring whether their spacecraft might actually be in a useful position to observe it as it passed relatively close to Mars. According to the China National Space Administration, engineers spent weeks running calculations and simulations, working out the comet's expected brightness, size, and path across the sky, and testing whether HiRC's normal capabilities could be adapted for a completely different kind of target. This wasn't trivial. HiRC was never designed to track a faint, fast-moving object like this. Its usual role involves short, precisely timed exposures of a bright surface passing steadily beneath the orbiter. Tracking 3I Atlas required something else entirely: long exposures, while keeping the camera locked steadily on a target that wasn't sitting still relative to the spacecraft's own motion. Engineers reprogrammed the camera to use exposures lasting around 30 seconds, a huge change from its normal operating mode, while simultaneously fine-tuning the spacecraft's orientation to keep pointing accurately at a target moving very differently from the Martian surface below it. And here's where the numbers get genuinely impressive. At the time of observation, 3I Atlas was moving at a relative velocity of roughly 58 kilometers per second. Tianwen-1 itself was moving even faster, at around 86 kilometers per second, in its own orbit around Mars. Both were also faint and fast in a way that made this observation exceptionally difficult. The comet's nucleus is estimated at only about 5.6 kilometers across, and 3IATLS appeared somewhere between 10,000 and 100,000 times fainter than sunlit features on the Martian surface that HiRC normally photographs. Despite all of that, the team succeeded. Between September 30th and October 3rd, 2025, across 3 separate observing sessions, Tianwen-1 captured real images of 3IATLAS from a distance of roughly 29 million kilometers, one of the closest observations of the comet achieved by any spacecraft. China's National Space Administration released these images and an accompanying trajectory animation in early November 2025. So what do the images actually show? They show exactly what you'd expect from a genuine, active comet. A visible coma, the cloud of gas and dust surrounding the icy nucleus, released as the comet warms while approaching the sun. and a visible tail streaming away from the nucleus in the direction shaped by solar radiation and the solar wind. That's it. No unexplained inversions. No brightening from the wrong side. No structure suggesting anything artificial. Just a comet, behaving like a comet, captured from an unusual and genuinely useful vantage point. Here's why that vantage point actually mattered scientifically. And it's a more interesting story than anything invented. Because Tianwen-1 was orbiting Mars. It observed 3I Atlas from a position significantly out of the comet's own orbital plane. A different angle than what ground-based telescopes on Earth, or even Hubble and Webb in Earth orbit, could provide. Researchers analyzing the images noted that this off-axis vantage point gave them a unique constraint on how dust was actually moving and distributed around the comet. Something harder to determine when every other observation comes from roughly the same general direction. Scientists studying the 3 observing sessions found clear changes in the shape of the coma and tail across just those few days, driven by the rapidly shifting viewing geometry as both the comet and the spacecraft moved along their own paths. By comparing these observations against something called Finsen-Probstein dust dynamical models, a well-established method used to study how dust particles disperse from an active comet under the combined influence of gravity and solar radiation pressure, researchers were able to estimate the size of the dust grains that made up the coma. Their analysis suggested the coma was dominated by relatively large dust grains, on the order of a few hundred micrometers across, roughly the width of a few human hairs. That's a genuinely useful, concrete data point about the physical nature of the material this ancient comet is shedding as it passes through the inner solar system. None of this required hollow structures, internal chambers, or anything suggesting the object wasn't a completely natural comet. Every single measurement fits standard, well-understood cometary physics. It's worth pointing out that Tianwen-1 wasn't even the only spacecraft orbiting another planet to capture. 3-1 ATLAS, the European Space Agency's Mars Express orbiter, and its Cassis camera, also imaged the comet during roughly the same period, using different instrumentation and a different set of exposure times. Having multiple spacecraft, positioned around a completely different planet than Earth, independently imaged the same interstellar object gave researchers additional cross-checks on the comet's brightness, structure, and behavior, all of which reinforced the same basic picture rather than contradicting it. So why did China's space agency treat this as such a significant achievement, if the resulting images themselves were relatively modest, faint, and grainy? Because the real accomplishment here wasn't really about 3I Atlas at all. It was about proving that an orbiter built entirely for one specific job, photographing a planetary surface, could be creatively repurposed on short notice to track a completely different kind of target. Faint, fast, moving against an unfamiliar background, using exposure techniques the camera was never originally designed for. According to the China National Space Administration, this observation campaign was treated internally as an important extension mission for Tianwen-1, valuable specifically because of the technical experience it provided. That experience is expected to directly inform China's next deep space mission, Tianwen-2, which launched in May 2025 and is currently on its way to sample a near-Earth asteroid. In other words, the real headline isn't that Mars saw something Earth couldn't explain. It's that a 14-year-old in space years, Mars orbiter successfully pulled off a genuinely difficult engineering challenge, tracking one of the rarest objects in the solar system using a camera built for an entirely different purpose. And in doing so, contributed a small but scientifically valuable piece to the broader, ongoing, cooperative effort to understand 3I TLAs. That broader effort has involved researchers and telescopes across the globe. NASA's Hubble and James Webb telescopes studied the comet's chemistry in detail, finding an unusually high carbon dioxide content and later detecting methane venting, findings that pointed to an object formed in a chemical environment very different from our own solar system. Billions of years ago. A study published in Nature in June 2026 used isotopic ratios inside the comet to estimate its age at somewhere between 10 and 12 billion years old, making it one of the oldest individual objects ever directly studied by human instruments, roughly 3 times older than our own solar system. None of that research from NASA, from ESA, or from China's own space program suggests anything artificial or unexplainable about 3I TLAS. Every finding fits the picture of an extraordinarily ancient, but entirely natural interstellar comet. It's worth addressing directly why this story got exaggerated so heavily online in the first place. 31ATLA's genuinely is an exceptional object. It's rare. It's ancient beyond almost anything else humans have directly studied. It came from somewhere else in the galaxy entirely, and it's leaving again forever. That's already remarkable enough to generate enormous curiosity, and unfortunately, that curiosity makes it an easy target for invented claims about hidden structures, secretive government withholding of data, or objects behaving with intention. None of that is supported by anything in the actual publicly released scientific data from any space agency involved. The real story requires no invention at all. A genuinely ancient piece of another star system happened to drift close enough to our own from multiple space agencies, working independently and cooperatively. To study it in detail using an unprecedented range of instruments, from powerful space telescopes to a repurposed Mars surface camera tens of millions of kilometers away. So here's where things actually stand. 3I Atlas has already passed its closest approach to the Sun and continues moving back out toward interstellar space on its one-way trajectory. Tianwen-1's images, alongside data from Hubble, Webb, and ground-based observatories worldwide, have all been folded into a growing collaborative body of research about this object's composition, structure, age, and origin. That research paints a consistent, coherent picture. An ancient comet formed somewhere else in the galaxy roughly 10 to 12 billion years ago, drifting silently through interstellar space for most of the Milky Way's history, before briefly passing close enough for humanity's best instruments on Earth, in orbit, and even circling another planet, to study it before it's gone for good. That's the actual story. No fabricated inversion, no hidden intention, no data China hesitated to release out of fear. Just careful engineering, genuine international scientific cooperation, and one of the most remarkable objects ever studied passing quietly through our solar system on its way back out into the dark. If you want to keep following what researchers find as more data from 3I Atlas continues to be analyzed, subscribe and turn on notifications. The real universe keeps turning out to be strange enough on its own, without anyone needing to invent anything extra to make it interesting. There's another reason this discovery matters long after 3I Atlas has disappeared beyond the reach of our telescopes. Every interstellar object scientists successfully study becomes a reference point for the next one. Instead of starting from scratch each time, researchers can compare chemistry, structure, activity, and orbital characteristics against previous visitors to determine what they have in common and what makes each one unique. Right now, the sample size remains incredibly small. Before 2017, humanity had never confirmed an interstellar object passing through our solar system. Then came Oumuamua, followed by 2I Borisov, and now 3I Atlas. 3 objects aren't enough to describe an entire population spread across the Milky Way, but they're enough to reveal that these visitors are probably far more common than scientists once believed. The reason we detect so few isn't because they're exceptionally rare. It's because space is unimaginably large, and most interstellar objects are likely too small, too faint, or moving too quickly to be discovered before they've already passed through the inner solar system. Every improvement in telescope sensitivity increases the chances of spotting these ancient travelers earlier and studying them in much greater detail. That's exactly where astronomy is heading. New survey telescopes are being designed to scan enormous sections of the sky night after night, automatically searching for faint moving objects that older surveys might have missed entirely. As those observatories begin operating at full capacity, astronomers expect the number of known interstellar visitors to grow steadily rather than appearing once every several years. That shift could completely transform this field of research. Instead of treating every discovery as a unique scientific event, researchers may eventually begin classifying entire families of interstellar objects, identifying common chemical signatures, comparing their origins, and learning how planetary systems across the galaxy form and evolve under different conditions. Some may prove rich in water ice. Others could contain unusually high concentrations of carbon compounds or complex organic molecules. Some might originate from young planetary systems still actively forming planets, while others, like 3I Atlas, appear to preserve material dating back to the earliest chapters of our galaxy's history. Every new detection broadens that picture. It's also worth appreciating what made this particular investigation possible. No single telescope, spacecraft, or nation solved this puzzle alone. Ground-based observatories first detected and tracked the object. Space telescopes measured its composition across different wavelengths. China's Tianwen-1 contributed observations from Mars orbit. Independent research teams analyzed the data, compared results, challenged one another's interpretations, and gradually assembled a remarkably consistent scientific explanation. That's how modern astronomy increasingly works. Discoveries of this scale depend on international collaboration, shared observations, open scientific discussion, and repeated verification. Individual missions may belong to different countries, but the scientific questions they address belong to everyone. The universe doesn't recognize national borders, and neither does the evidence collected from it. Perhaps that's the most enduring legacy of 3I Atlas. It reminds us that even an object which spent billions of years drifting silently between the stars can become a source of shared human knowledge once it briefly enters our cosmic neighborhood. For a short period, observatories around the world turned their attention toward the same tiny visitor, each contributing another piece to a much larger scientific story. Years from now, researchers will almost certainly continue publishing new analyses using data already collected during this flyby. Better computer models, improved laboratory measurements, and future discoveries of additional interstellar objects will all provide new context for interpreting what 3I Atlas has already revealed. In that sense, its scientific journey is only beginning, even though its physical journey through our solar system is already ending. As it continues back into interstellar space, it carries nothing away from us except reflected sunlight. What it leaves behind is something far more valuable: evidence, real measurements, verified observations, and another reminder that the universe is filled with extraordinary natural phenomena that often prove even more fascinating than the fictional stories built around them. If you enjoyed this deep dive into the real science behind 3I Atlas, make sure to subscribe and turn on notifications. We cover the biggest discoveries in space, astronomy, and planetary science using verified research, real observations, and the latest findings from missions around the world. Thanks for watching, and I'll see you in the next one.